For our final talk of the day, we have Luca Iliesiu telling us non-perturbative gravity.
That was an intention. Thank you very much for the invitation. So today I'll be talking about the non-perturbative Hilbert space of gravity. This is work done in collaboration with Adam Levine, who's right here. So ask him questions as well if you want. Henry Lin, Henry Mansfield, and Mark Metze. It's to appear. So in the past couple of years, we have made a lot of progress in understanding black hole microstates from the gravitational path integral. But today's talk will not focus about the microstates themselves. It will focus on whether we can use the same techniques to understand the interior of black holes. So our concrete goal today is to understand the bulk Hilbert space by defining a valid inner product that includes non-perturbative corrections in 1/g for any two given interior states, let's say an out state and an in state, that are specified in terms of gravitational variables. And given an in state and an out state, we want to be able for the path integral to compute the actual transition probability between the two states. And to be more specific, in JT gravity or in JT gravity with matter, we'll propose a way in which summing over topologies will modify the inner product, leaving the underlying vector space unchanged. And by understanding the modification to the non-perturbative modification to the inner product, what we'll be able to do is to also define bulk operators. So we'll define bulk operators by inserting an operator in an inner product and slicing up our space-time by inserting the ket and the bra for every given operator. And given some definition for an operator that's specified in terms of these coefficients, Oj, in a given basis, what we hope to do afterwards is to determine what this operator represents at the path integral level and make sure that it's a deep invariant operator, even when including non-perturbative effects. So to be less abstract, I'll try to exemplify the power of the formalism that I'll present by focusing on two related observables. So the two related observables both have to do with a perturbation that is turned on in the thermal field double state on one side that an observer on the other side could potentially see when they fall inside of the black hole. So let me just present what happens in this setup. In this setup, famously, if the observer falls in at negative times, he collides with this perturbation with a very large relative center of mass collision energy. So it's dangerous to fall into such black holes. While if an observer falls in at positive times, it's seemingly safe to fall into such black holes because the observer doesn't collide with the shockwave that's sent in from the other side. Now, this picture is completely classical, and quantum mechanically, we have to wonder a bit whether this situation is correct or not, because I can write whatever state I have at positive times as a linear combination of states at negative times. So if we decide that it's safe to fall into a future black hole, we also have to explain the statement. So we're going to try to explain the statement in JT gravity, where the singularity structure is a little bit different. The particle and the observer and the shockwave always collide before they hit the singularity. Nevertheless, we'll still be able to test this statement of how states in the future that have an observer and a shockwave can be written as linear combination of states in the past. So the two observables that I'll concretely consider, the first is the length operator and its conjugate, its canonical conjugate, the speed operator. So in JT gravity, at negative times, the length starts out being positive. I showed it here, but it decreases linearly with time, which means the expectation value of a velocity, semi-classically, associated to this length is negative. And this is what people have called the white hole phase. It's when the size of the Einstein-Rosen bridge is decreasing. Then at t equals 0, this length is minimized, after which it keeps increasing linearly, and it has a positive speed after some transient time given by the thermalization time. And this is what people call the black hole phase. Nevertheless, at very late times, this observable is expected to saturate and plateau. This causes a little bit of a confusion, because if the length plateaus, then the average speed goes to 0. So you might wonder whether your state is actually a linear combination of a black hole state and a white hole state. And you might wonder whether this question even makes sense at late times. Perhaps the velocity operator has different eigenvalues altogether, and at very late times, it's just not true that it's a linear combination of the two phases. So to be very concrete, what we'll try to do is define these two operators and determine the probability distribution that we see a certain length and that we see a certain velocity. So this is just a proxy for what happens when the observer V and the particle, the shockwave on the other side, collide. So we want to make sure that this proxy is exact. So the second observable that we consider is, in JT with matter, we'll actually consider the center of mass collision energy between the observer and the particle. So here it's semi-classical expectation value. The center of mass collision energy actually grows exponentially with time. But we want to understand what happens what happens to this operator and to its associated probability distribution when we include perturbative and non-perturbative effects. Great. So let me start with a review. So to study these questions in JT gravity, we will focus on a set of states defined by slices that have 0 extrinsic curvature, so geodesics, and fixed proper length, where the renormalized length I'll call tilde L. The overlap between such states is computed in the energy basis is computed by considering the path integral that goes in between a boundary with fixed ADM energy and a slice that has fixed proper length. And this wave function that I'll denote by phi of L is typically referred to as the half-disk wave function. So the way in which one can compute this wave function is by seeing that it's actually an eigenstate of the Hamiltonian. The Hamiltonian on the left is the same as the Hamiltonian on the right. In pure GT, and the Hamiltonian takes this very nice form of a Liouville quantum mechanics. This can be derived from the Schwarz in action and has been derived in several papers. Good. So one can solve this differential equation explicitly, and one finds that this wave function is given by this Bessel function with an argument that's exponentially decreasing in length. So this Bessel function tells us the following, that if instead of considering the overlap between L and E, we consider the overlap between two L's, using the orthogonality of these Bessel functions, one finds that these two states are exactly orthogonal to each other at a perturbative level. And the meaning of this is fairly clear. On a hyperbolic disk, between any two boundary points, there's actually a unique geodesic going between them. So because there's a unique geodesic, this enforces that the length of the two geodesics coincide. So how about when we include higher genus corrections? So our proposal is to change the inner product by considering the same slices in the bulk, but including all possible processes of topology change in between these two slices. And we'll see that actually this defines a valid inner product. So at leading order, at order 1, we just get the same delta function that I showed to you before. But at subleading order, I get all sorts of higher genus corrections, which can be computed from these moduli space volume of Riemann surfaces with various genus. So, and in terms of these half-disk wave functions. So I could have written higher and higher orders in e to the S naught. But actually, if one resums the entire e to the s naught series, one finds a very simple expression. One finds that this inner product is given by an integral over the energies, where instead of the leading density of states, it's replaced by the average density of states in JT gravity, which itself has a e to the s naught expansion. So the reason why these two states are not orthogonal is because this average rho is not given by just a sinh, it's given by a sinh plus exponentially subleading corrections. So we believe this computes the average inner product between these two states. And similarly, one can compute higher moments of inner products between any set of L's, between L1, L2, L3, L4, and so on. And this doesn't only receive corrections from delta functions that show that these states are orthogonal, it also receives corrections from all sorts of multi-boundary or higher genus wormholes. And once again, you could write all of this in terms of the moduli space volumes of bordered Riemann surfaces. But again, the result highly simplifies when we write things in terms of the density of states. Namely, this complicated statistics of a product of inner products is given by the average of n of these densities of states times the average times 2n half-disk wave functions evaluated at different energies and different lengths. So the fact that we know all the statistics of these inner products means that there is a well-defined notion of what the inner product is within each member of the JT ensemble. Namely, within each member of the JT ensemble, the inner product between two of the L's is given by a sum over all energies in that ensemble times the product of these two half-disk wave functions. And the state L can be written as a linear combinations of the state EIs that are the eigenvectors of the Hamiltonian. Great. So the only thing we have to check is whether this is actually a valid inner product. So the first two conditions, the conjugation and the linearity of an inner product, are trivially satisfied in this example. The thing that's slightly non-trivial is the positivity of the inner product. So we want to consider some arbitrary state psi that can be a linear combination of all our ket states L for some function psi of L. And if one uses the previous values for the inner product between L1 and L2, one finds the following expression for the norm of psi. It's just a sum over squares of these functions psi tilde, where this function psi tilde is just the transform of psi of L with respect to the Bessel function. So this, because it's a sum over squares, is automatically positive when psi tilde of EI is non-zero for at least some EI. So this also tells us that there are null states. Namely, the null states in this model are given by the functions psi of L, whose transform psi tilde exactly vanishes on all the energies in a given ensemble. So this just determines all the null states in the Hilbert space. So they're not the physical states. And it also provides a concrete example of a non-isometric code in this model. Namely, the non-isometric code is simply the map between the perturbative Hilbert space and the bulk Hilbert space that has the property that when you apply the operator V that defines the code on all null states, it gives 0. So to briefly summarize what we've said so far, the basis L is overcomplete. The basis L that was orthogonal at leading order is secretly overcomplete. And nevertheless, even though it's overcomplete, when you include higher genus corrections, the path integral computes a well-defined inner product. So given that the basis L is overcomplete, we now have a problem in defining bulk operators. Namely, it's clear that there does not exist an operator L hat whose eigenvalues are the different values of L that we saw in perturbation theory that range between -infinity and had a continuous spectrum. So instead, there's an ambiguity in defining these operators. There are many different operators that agree with L perturbative at leading order, so at disk level, but disagree with the operators when including non-perturbative corrections. And here's an entire class of examples of such operators that are specified in terms of some arbitrary functions. Tilde f of L, if you actually look, this tilde f of L cancels this f inverse at this order, and this operator agrees perturbatively, but all these operators have different eigenvalues and eigenfunctions non-perturbatively. And this actually maps to a different ambiguity that we sometimes encounter. Namely, it maps to a path integral ambiguity. If I want to define a length operator on a hydrogenous surface, I have to decide how I weigh the different geodesics that go between two boundary points relative to each other. So we'll see in two examples that these two ambiguities kind of map to each other. So the first example of the simplest operators that captures the length is just the integral over L itself. So this is what you would write at perturbative level in either case. To compute, let's say, the expectation value of this operator in some arbitrary eigenenergy state E1 and E2, then what we have to do is insert the operator L and cut the boundaries that have asymptotic conditions where the ADM mass here is fixed to E1 and here to E2, and sum over all possible resulting geometries. So at order, just to give you an example, at order e to the minus 4s naught, there are three kinds of geometries that contribute. One that has a genus 2 surface on either the inner product between the bra and L or the L and ket, two genus 1 surfaces, or a cylinder that has a genus 1 surface. And for each surface, you have to do a distinct path integral over metrics. Sorry about that. But if I want to if I perform this integral over L and try to rewrite that as a single path integral over metrics, what one finds is because of the quotient by large diffeomorphisms, the gluing of this geodesic segment, this red geodesic segment in the figure on the right, gives rise to multiple geodesics on a homogeneous surface. It gives rise to both this geodesic and the twisted geodesics that are obtained by taking this geodesic and applying all possible then twists. And doing the same for all the other surfaces, we actually obtain all the geodesics on the surface. So in conclusion, this inner product actually computes a sum over all geodesics that are all just weighted by their length. And this is actually some computation. The computation for the expectation value of this operator was the exact definition that I considered in an earlier paper with Metze and Sarosi. But the thing that we saw before is that the definition of the length operator is not unique. We can consider multiple definitions at the Hilbert space level, all of which are equally good. So for instance, we can also consider the length operator as if it was measured by a 2-point function. So namely, consider a length operator that's defined by an integral over dl e to the minus delta L and taking a log. So exponentiating this operator, this precisely following the same argument that I discussed before, this precisely gives you the 2-point function in the theory. And using the fact that this L hat operator has the same eigenfunctions as e to the minus delta L hat, but eigenvalues that actually correctly capture the length of the different geodesics, we can conclude that what this operator actually is measuring are the lengths and eigenfunctions that are associated to a 2-point function O left or right, where O is some operator of mass delta. And the special thing about this geodesic is that, about this definition of the operator, is that L hat puts greater weight on short geodesics as delta grows, right? That's because the 2-point function itself is dominated by shorter geodesics. Good. So enough formalism. let's actually compute various properties of these observables. So this observable, because of this logarithm, turns out to actually be very difficult to compute analytically. But the nice thing about this formalism is that we can actually perform a lot of numerical computations. So we can numerically compute the matrix e to the minus delta L for some energies E1 and E2. Here, you can compute analytically what each matrix element is, where E1 and E2 are sampled from one member of the JT ensemble, for which I showed an example of an energy histogram here. So this is approximately the Sinh density of states, but also includes the non-perturbative corrections, but it's one member of the ensemble. And we'll study this state in some microcanonical energy window, and we'll study its expectation value, its velocities, and so on and so forth. So I won't go into too much detail about the numerics, but let me just say that the numerical results are largely insensitive to what we choose delta to be, as long as we choose it large enough. What we choose the energy cutoff in the JT ensemble to be, of course, we cannot sample a full JT ensemble that has an infinite number of energies, so we have to choose some energy cutoff. And what we choose the size of the matrix to be, from which we sample. But for concreteness, here are the values that I'll be showing numerics for. So we'll choose delta equals 1, energy cutoff 6, size of the matrix 500, and occasionally I'll show both results in a single member of the ensemble, but also ensembled average, with the size of the ensemble being 100. So before I discuss expectation values, let me just discuss the spectrum of the length operator. So we put this operator on a computer, diagonalize it. What are its eigenvalues? So one interesting thing that you already see in the spectrum of L hat is that the operator, the eigenvalues are bounded from above by a number that's of order e to the s naught. So this already indicates that if we compute the expectation value of this operator, because its eigenvalues are bounded, the operator will plateau. Similarly, we can compute the spectrum of the speed operator that's obtained by taking the commutator with the Hamiltonian. And this one has an unbounded spectrum. That's because the higher the energy of the state, the greater the speed of that state is. But if we project to the energy window that we study, we find something very interesting. Number one, we find that the spectrum is bounded from both below and above, a fact that is not true at perturbative order. And we also find that the eigenvalues come concentrated around these two lines that are given by the square root of the energy. This is actually the semi-classical value for a white hole speed and a black hole speed that we saw earlier. So the fact that the most eigenvalues come in these two clumps suggests that the concept of a black hole and a white hole might make sense even non-perturbatively. So next, before we discuss expectation values, let's discuss time evolution. So let's try to see what the Hamiltonian is, not in the L1, L2 basis, that's not orthogonal, but in the basis of eigenfunctions of this operator, L delta. So perturbatively, the Hamiltonian is almost diagonal in the L1, L2 basis. It's only slightly off diagonal because of the second derivative of a delta function. But non-perturbatively, what we find is that because of the change of basis between these L's and the actual eigenfunctions of the L operator, the Hamiltonian in expectation value acquires non-zero elements away from the off-diagonal. So that means that even if we start out with a theory whose ADM Hamiltonian seems local in the metric degrees of freedom, because of these non-perturbative corrections, we end up with a Hamiltonian that allows for transitions between distant lengths. So now let me actually show you what the probability distribution over the eigenvalues of this length operators are. So I'll show a little video. So this is for a fixed member of the ensemble, where the value 1,000, a bit over 1,400, is the maximum eigenvalue of the length operator that we find. So as we start, we see a wavefront that moves linearly with time, but once the time passes a scale that's of order e to the s of e, the entropy at energy e, we find that the wave function completely decoheres and has support as a non-zero probability for all eigenvalues of L, all kind of equally likely. So this leads to the following expectation value. It does go negative. I only showed it on positive eigenvalues here. So the expectation value of L therefore takes the following form. It grows linearly with time as predicted by at the semi-classical level, after which it has this little hump and then plateaus. So this is an ensemble average result. So similarly, we can now look at the speed, and this is a similar result that we found in the paper with Metze and Sarasi. The difference is that there we also got a divergent constant piece, which seemingly depended on delta. But the result seems universal. Even if we change delta, this plateau and the linear growth seem fairly reliable. So now let's discuss the speed probability in a fixed energy window. So again, we'll start with a fixed ensemble member, and the t equals 0, this probability is symmetric because we're right at the turning point. We're right at the point where the average of v is 0. But very quickly, almost instantaneously, we're dominated by the black hole phase. Once we reach e to the s, the probability kind of oscillates between the black hole phase and the white hole phase. And you see these two peaks over here. So this can be clearly seen if I look at the average of the speed that I plot here in blue, and at the average of the speed if I only select for speed eigenvalues that are positive versus speed eigenvalues that are negative. So here you see, and the dotted red and dotted green lines are two sigma intervals in which I have either positive speeds or negative speeds. So the fact that these two bounds exist, and I don't instead have a random plot for positive speeds and negative speeds, suggests that at very late times, I'm in a linear combination of a black hole and a white hole phase. And this can be seen by plotting the probability that the speed is positive versus the speed is negative. You obtain this very large, very nice 50-50 chance of seeing a black hole or white hole state at very late times. And this should be compared to the results of Stanford and Yang that did a similar computation, but with a slightly different definition of the length operator on the handle disk. So to briefly summarize what I've talked about so far, we can now understand Born's rule for the bulk Hilbert space of JT gravity, even at a non-perturbative level. Crucially, we have to be careful about redundancies in the bulk Hilbert space when states are defined in terms of low energy EFT variables, namely in terms of these lengths. This leads to ambiguities in defining operators associated to gravitational observables, which map to similar ambiguities at the path integral level. Even with such ambiguities present, our results seem universal, namely the length always plateaus and the probability of encountering a black hole or white hole phase always seems to be 50-50, regardless of what we choose delta to be. We haven't checked for different functions, but presumably similar things happen. So next, we want to ask whether the same things are true in the presence of matter fields. So more concretely, what we want to do is prepare the actual state in JT gravity with matter, where we insert the perturbation V that corresponds to the observer and the perturbation W that corresponds to the shock wave, take some time slice in the future of when these two operators are inserted, and ask what center of mass collision energy would I detect on that time slice. Now, regardless of what the time slice is, the center of mass collision energy is the same. It's invariant under changes in time. That's what I want to detect. I want to detect this probability, and this probability is not known even perturbatively. Good. So to actually compute these overlaps, one can use the decomposition of the Hilbert space of the theory into a product of the L-state Hilbert space and the matter Hilbert space. David Kolschmeyer talked about this yesterday. So ADS2 has an SL2R isometry that acts on matter fields. It moves matter fields around. So representations of the matter Hilbert space, states in the matter Hilbert space can be arranged in terms of representations of SL2. So one way of arranging representations of SL2 is in terms of the Casimir operator C hat, where this is the eigenvalue of the C hat operator, and delta is the scaling dimension of whatever operator I insert. And there's actually a one-to-one map between the center of mass collision energy and this operator C hat. Namely, if I consider the overlap, a state in which I insert the operators V and W, I have to decompose this state into eigenfunctions of the operator C hat. And the center of mass collision energy is simply given by the mass associated to this composite scaling dimension that corresponds to inserting this double trace operator on this time slice. And the center of mass energy at very large values of n is approximately given by n itself. The important thing, though, is this quantity n that we encounter here is actually quantized. Double trace operators here have integer n. So the center of mass collision energies that I can possibly detect in ADS2, or the values of the Casimir that I can possibly detect in ADS2, are related to these values of n when I have these two states. And these overlaps have actually been computed perturbatively in these papers and are given by a generalization of the half-disk wave functions that I showed earlier. They're given by a set of Wilson functions instead of being given by Bessel functions. So using these Wilson functions and performing the right integral over energies, we can get to the kinematic regime that we're interested in, namely a regime where we insert these operators V and W separated by some Euclidean distance as well as some Lorentzian evolution that captures at what time I'm throwing in the observer. And we can compute the probability P of n explicitly. We find that this probability has support only at very large n. And it's given by a Gaussian distribution, but it's not a Gaussian distribution in n, it's a Gaussian distribution in log n. The median of this Gaussian distribution grows linearly with time, and its width also grows linearly with time, but with a coefficient that makes the Gaussian be very much separated from negative values of log n. So the width is much smaller than the median at large values of beta. Sorry, at small values of beta. So one thing that's already interesting about the Gaussian probability distribution in log n is the fact that if I compute the expectation value of n, this is dominated by the tails of this distribution. So there is a breakdown of the semi-classical result that occurs fairly quickly. But that's not the most interesting effect. The most interesting effect is that at times that are of order S0, so not e to the S0, there are actually e to the 2S0 states whose probability is less than e to the minus 2S0, including this peak of the distribution. So the maximum probability in this plot at times e of order S0 is actually e to the minus 2S0. So this competes, this probabilities that are all of order e to the minus 2S0, all competes with the non-perturbative corrections that the overlap between VW and the state in which I insert this double trace operator, it competes with the non-perturbative corrections to these overlaps that come from these types of wormholes, where I insert the operators VW and the double trace operators on the same side. And similar wormholes actually lead to a violation of the conservation of the Casimir with time. So what this is telling us is that at times of order S naught, the overcompleteness of the n basis can be detected, and I should be able to tell the fact that n is no longer a quantized quantity. Well, however, if we don't care about quantized values of n, non-perturbative effects are not that important at this time that's of order the page time. Instead, if I define a coarse-grained value of n, if I only am not interested in detecting individual values of n, but detecting what n is up to some epsilon%, we find that that non-perturbative effects are not important, and instead the probability P of n is given by the probability of detecting a certain length where the length is related to n, just log n. I'll just take one more minute if that's okay. Okay. Great. So this allows us to speculate about what the expectation value of the center of mass energy is at very late times, namely that it plateaus at the time of order e to the s naught. So to summarize, just like in pure JT, in the presence of matter, the overcompleteness of the bulk Hilbert space is important. To quantize the values of n, I need to see the values of n being quantized, I need to be at times that are smaller than the page time, but a complete breakdown of the observable only occurs at the time that's order e to the s naught. So let me end with a list of open questions. The major unanswered open question that we have is, how does a bulk observer resolve these ambiguities between the different non-perturbative definitions of a bulk operator? Does it depend on the experiment they perform? So for instance, here we measured the Casimir on an entire time slice, but perhaps an observer should only make a local measurement of their stress tensor. And the outcome might even depend on the calorimeter that they carry. Does the notion of an observer making such measurements even make sense at late times? Well, there is a probability that the observer disappears. There is some overlap between states in which the observers exist and states in which different matter excitations exist. So perhaps, at very late times when all the states have very small probability, there's not even a notion of the observer that's worth talking about. Do the operators that they measure act linearly on the Hilbert space that we defined? Here we kind of assumed that a priori, but it would be nice to prove that more explicitly. Namely, it will be nice to prove that whatever operator an observer tries to measure still maps null states to null states. So for any such question, we hope that the formalism that will develop will help offer some answers. Thank you very much.
At some point, this length operator becomes a length operator as a function of this. Why the length depends on the function.
So the way in which we define this, it's just part of the definition of this length operator. But the way to physically view it is that you could take, let's say you have some field of scaling dimension delta in your theory. And you try by computing overlaps between E1, your operator E2, you try to measure all the eigenfunctions of this operator. That's so those eigenfunctions you can then use to construct a length operator. And that's why the operator depends on delta. It's because the 2-point function itself of E1, O, E2 depended on delta. Right? E1, O left, O right, E2 depended explicitly on delta. The interesting thing that we find is that the delta dependence is very weak. As delta is large enough, basically changing delta only shifts these plots by kind of a constant amount. It doesn't actually change the time dependence. And the plots are seemingly convergent as we make delta large. Perhaps the interpretation of this is that the spacing between geodesics, consecutive geodesics on these Riemann surfaces becomes very large at large Lorentzian times. So I have some minimal geodesic, a second geodesic, and third geodesic. They're all suppressed by powers of delta. So, as long as the spacing between geodesics is quite large, I don't need that large of a value of delta to suppress longer geodesics.
When you included matter, if I understand correctly, you continue to use the wave functions of the empty wormhole.
What do you mean by empty wormhole? No,
the Bessel functions.
No, we did not. We used these Wilson functions.
Sorry.
Which are just, this is just written that it's an analog to the Bessel function. But it's a more complicated function that kind of morally computes the OP coefficient between VW and this double trace operator. And there's many ways of rewriting these overlaps depending on the pages that I'm interested in studying. So yeah, go ahead.
Is it reasonable to consider these non-perturbative corrections, but not considering matter loops, for example?
We don't know. I think in a fixed member, one suggestion is that in a fixed member of the ensemble, we might still consider these energies to be chaotic, but still keep the same functions in the probability distributions of that. But we don't exactly know. One thing that I might say is that the statement about funniness happening at the page time, the fact that this wormhole correction becomes important, I think is fairly reliable, regardless of whether or not I consider matter loops around these cycles. That's because these types of wormholes, as I'm sure you know, are saddle points. So these types of corrections are reliable. And yeah, the perturbative correction itself is, I think, also reliable. Yeah.
So another way you could try to define black holes or white holes is you could say that a black hole is a state where at some time in the, say, the not too distant past, say less than e to the s naught, if you run backwards in time, there's some huge shell that comes out. And that the black hole, that the black hole was made out of, right? It's like formed by some short collapse. Whereas the white hole is the time reverse of that. It's some state which in the future is gonna spit out a shell and there's not gonna be any black hole for a sec.
Yeah.
But I would guess that actually most states are neither of these things. Like probably most states in the CFT Hilbert space, like there's never like a time where it's like definitely gonna.
I completely agree with that, and I share your opinion. The only thing that is very surprising, well, one thing that's very surprising, at least to me, that I found is that when you look at the speed operator, at the spectrum of the operator itself, you find that it has these two clusters of eigenvalues.
I would have guessed that there would be other states where it's just kind of zero.
Well, that's not what we find.
Yeah.
Like this is just, I don't know how to compute this analytically. This is just what comes out of the numerics. It didn't have to come out into these two clusters. You could expect to reproduce the semi-classical results, even if you have very few eigenvalues here and very few eigenvalues at the bottom, and a lot of eigenvalues at random values in between.
I just like to understand,
Well, your definition is very different than this definition.
Yeah. I mean, I guess, but yeah.
Any questions? All right, let's thank Luca again.